The video today is on colligative properties. Now, colligative property is a property of a solution that depends on the number of solute particles that can be present in the solution. One of the things that we have to figure out when we do our colligative properties is find the number of moles of particles, which we're going to be getting from just the formula. So it's really the number of moles of particles per mole of solute. And this is called the Van 't Hoff factor. Symbol is a small I. Now there are three colligative properties we're going to be checking out. We're going to take a look at freezing point depression, boiling point elevation, and osmotic pressure. Now here's a here's a picture showing you that when you dissolve a lot of sugar in water, let's say to make candy, it really raises the boiling point of the water. If you notice up here, the boiling point is well above 100 degrees centigrade. So the boiling point has been elevated or raised by dissolving sugar in it. In the wintertime, we spread salt on the highways to help melt the ice. And that works because it winds up lowering the melting point of the ice. And so the ice, instead of melting at 0 degrees, will melt below 0. And once it melts and it becomes liquid water, it can evaporate much quicker. Also, people add antifreeze to a car radiator, and this does two things. It lowers the freezing point of the water that's mixed with it so that it won't freeze in the winter, but it also raises the boiling point of the water so that in the summer, the antifreeze mixture doesn't boil off. And years ago, you used to see a lot of cars in the summertime pulled over to the side of the road with steam escaping from the cars. You very rarely see that today. Now, the first thing we have to be able to do is figure out how many moles of particles are produced, because this is going to give us that Van 't Hoff factor. So we have three different solutes that we're going to be checking out today. We have sugar, which is a non-electrolyte. We have sodium chloride and calcium chloride, which are both strong electrolytes. So let's check out the sugar. So here we have some glucose in water. When you put glucose in water, we have a mole of glucose solid. When it dissolves in water, it doesn't produce any ions at all. It just gives us 1 mole of particles, 1 mole of dissolved molecules. Therefore, the Van 't Hoff factor here is going to be 1. And it's this one that we're talking about, this number 1. Now let's check it out for sodium chloride. The sodium chloride, we get 2 moles of ions, 1 mole of sodium and 1 mole of chloride. And that's going to give us an I factor of 2. And for calcium chloride, we're going to get I equals 3, because from calcium chloride we get 1 mole of calcium and 2 moles of chloride for a total of 3, so I equals 3. So that means that if you are going to compare these three solutes mole to mole, the calcium chloride would lower the freezing point and raise the boiling point much greater than the glucose or the sodium chloride will. All right, so let's check out freezing point depression. So here's the formula that we need to figure that out. Freezing point depression has the symbol delta TF, means change in the freezing temperature. And to calculate that, we have to get a constant, and the constant varies from solvent to solvent, molality, and we have to have I, which is the Van 't Hoff factor. So for the constant, we're just going to look that up. Mostly you'll be using water, but if it was a different solvent, we just look it up in a table. Molality, we'll have to calculate that, but we've already done that in an earlier video. So remember, this is not the freezing point. This is the change in the freezing point. To get the freezing point, we have to calculate the change and then take the change and subtract it from the normal freezing point of the solvent. This is one way that people make ice cream, is by making the mixture of ice cream get way below the point of water, and therefore it turns into a gel. Now for boiling point elevation, we have a very similar formula, only it's B for boiling, delta TB equals KBMI. So the only difference is it's a B for boiling. Now there is a difference in the constant. There's a different boiling constant from the freezing constant, even for the same solvent. So you can't use the same constant for that. Here's a difference also. Since the boiling point is elevated, to figure out the boiling point of a solution, we have to add the change to the boiling point, the normal boiling point of the solvent. So that means that water solutions as long as the solute is still present. Water solutions boil above 100 degrees, and freezing, let's see, those solutions when they're being frozen freeze below zero. So the changes are in both directions. And this is the table that you'll find in your textbook that lists boiling points, the boiling point constant. You see it looks like it has funny units, degrees times kilograms per mole. Well, kilograms per mole is really divided by molality, so it's really degrees per molal. Here's the normal freezing point, and then here's the Kf, freezing point constant. So let's look at for water. For water, the boiling point constant 0.51, but the freezing point constant 1.86. Quite a bit different. And look at, you'll notice that just about for all of these, except for ethyl ether, is about all the rest though. The freezing constant is much greater than the boiling constant. And here are our formulas down here at the bottom. So make sure that you write these down. All right, so I'm going to play with the formula a little bit. Here's my formula for finding the change in the freezing point. I'm going to make some substitutions like I did earlier. So M, molality, is moles of solute per kilogram of solvent. And moles of solute is grams of solute divided by the molar mass of solute. So I can, and I did this before, I can take this fraction here and put it in place of moles of solute. So we can replace moles of solute. And then I get this. Now I can take that and plug it into my overall formula. So if I take this now, I get this whole thing here and put it up in here and replace M with that. And I get this. Now you might say, well, this is too much for me to do, but really this one formula has everything in it. So if you copy this one out, in fact, I want to copy them all out, but this one especially here, because the most common kind of a question would give you grams of solute, and they give you the formula, you can calculate the molar mass. And you can easily get kilograms of solvent. Plus, you can also solve this formula for molar mass of solute, which it is many times. So I'd copy that one out and pay special attention to that one. So here's the first question. What are the freezing point and boiling point of an aqueous solution of 10 grams of glucose in 50 grams of water? I'm also going to answer the question, what if the solute were 10 grams of sodium chloride instead of glucose? So now for the first question. I'm going to copy out my formula that I showed you earlier. This has all the factors in it so we can see every one of them. Now for Kf, because it's water, that's going to be 1.86 degrees per molal. Grams of solute will be 10. I is going to be 1 because it's glucose. Now the molar mass of the solute will depend on the formula for glucose. So I'm going to calculate that by multiplying the subscripts by the atomic masses of the elements and then adding them up. And I get a total of 180 grams per mole. And I'm going to have to change my 50 grams of water to kilograms. So I'm going to move the decimal point 3 places to the left. And here's what I get. Now we can see what will cancel out. My pen here. So I can cancel out moles. Moles will be gone. Kilograms will be gone. Grams will be gone. And I'm going to be left with degrees centigrade, which is exactly what I want. So this represents the change in the freezing point. Now it's not the freezing point, it's simply how many degrees the freezing point will change. To find the freezing point, I have to subtract the change from the normal freezing point of water, which is 0 degrees. And therefore I get negative 2.07 degrees centigrade for the freezing point. You have to remember to do that because many times people just stop here when they get the change and they think they're all done. Now for the boiling point, I plug in my values. You notice the only thing that changed is my constant. This is Kb for water, 0.51 degrees. I know in some textbooks that might have a 2 after that one, but it's not going to make much of a difference here. And then we get, for a change in the boiling point of about a half a degree. Now what's the boiling point of the solution? Well, here we have to remember to add the change to the normal boiling point, and that's why we get 100.57 degrees. You don't want to do all of this math and at the end mess it up by either subtracting when you should add or adding when you should subtract, like up here. All right, well, what if the solute had been sodium chloride instead? Now I make my substitution. This is the same values I did before for the freezing point. Here's my constant, but it's 2 for I. I is 2, and that's the molar mass. Those are the two changes, I and molar mass, and I get a much bigger change in the freezing point. Freezing point then minus 12.7 degrees. What about the boiling point change? I plug my values in. Again, the only difference between the glucose question and this one is that I is 2 and the molar mass is much smaller, and I get a change in the boiling point of about 3.5 degrees. Therefore, the boiling point 103.49 degrees. So it makes a big difference if you use a compound with I greater than 1, then that is just 1. Now, when you do these experiments, this is what we expect to see for I. You notice it's all whole numbers. And the 2 and the 4, all these numbers give us the number of moles of ions we expect to see. But this is what we do see. You notice these numbers a little bit smaller than that. So what we see in reality is a little bit smaller than what we expect. What's going on here? Why the difference? Well, this is what's going on. Sometimes ions will clump together like this. So to make you a solution, a few ions aggravate or clump together, forming ion pairs that behave as single ions. So if I were to count these singly, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But because these guys have clumped together, even though they're bigger ions, a bigger ion pair, they act as only 10 ions. So that means that the more concentrated your solution is, the more that observed change in the freezing point will be different from what you calculate. And now for the third colligative property, osmotic pressure. So osmotic pressure is a pressure needed to reverse osmosis. Let's go through osmosis. So here we have a beaker with water in it. We have a container in here that the bottom of it just has a semi-permeable membrane on it, so it's kind of open there. But that membrane is enclosing a solution. And whatever the solvent is in the solution is the same as out here. So let's just say it's water, make it easy. So we set this up like that, and over time what happens? Well, water can move freely in both directions, in and out of that membrane. What we find happening over time is, though, more water enters through the membrane into the solution than comes out. One reason for that is there's simply more water molecules lined up on this side of the membrane than on the inside of it. So over time then, the volume increases in my container. Now, it's not going to keep on going. At some point it'll stop because gravity is trying to pull the solution back down to where it started off as. So the height difference between the height of the liquid in the tube to the height of the liquid on the surface here is what we call osmotic pressure. This is the formula for calculating osmotic pressure. The symbol is actually capital pi, although in some textbooks you might see small pi with the curvy hat. And then we have M for molarity. R is the gas constant, and you can see the units for the gas constant. T would be the temperature in Kelvin, and of course I we know is the Van Hoff factor. Now you notice now for R, that means we must have molarity because we want liters. We must have the pressure, or we're going to get the pressure in atmospheres for an answer, and we need Kelvin. Now here's another way to look at osmotic pressure. Here we have a pure solvent, and here we have a solution. Water is going to go in this direction here. Now, osmotic pressure can be defined as the pressure needed to stop or reverse osmosis, as we see here. So here is our pure solvent in the solution, semi-permeable membrane. What happens over time? Solvent moves into the solution and the volume rises. Now the pressure The osmotic pressure is actually the difference in the height of the solution in the two tubes. But it's not a height difference in mercury, it's a height difference in the solution. So if we were going to calculate that pressure, we have to know all those factors I mentioned earlier. So here's a question now based on that. What is the osmotic pressure of a liter of solution at 25 degrees centigrade that contains 5.85 grams of sodium chloride? Here's my formula. Now I need molarity. So molarity is moles per liter. So I'm going to start off with grams per liter, which they gave me in the question. A liter of it, then grams. And I'm converting it to grams, from grams per liter to moles per liter. This is the molar mass of sodium chloride. You can see then the grams cancel out, and I get moles per liter. So that's the molarity. Now I'm going to plug everything into my formula. So you see now I have, here's my molarity down here. Now this is R, this whole thing. And you notice we need to put the units with it because for canceling, here go the liters and here go the moles, just like that. Now here's the temperature in Kelvin, there goes the Kelvin. So remember, to get Kelvin, we're going to add 273 to the centigrade temperature, and that's why we get 298. And the 2, that's I, and that's because it's sodium chloride. And we multiply that out, and we get a pressure. This is our osmotic pressure, 4.89 atmospheres. Now, osmotic pressure is also used to find the molar mass of proteins, which can be extremely high. It can be in the hundreds of thousands. And so we saw really how we could use the gas constant to find molar mass of gases. I mean, one of the big things in chemistry is identifying unknowns, and you need to know a molar mass to identify an unknown. So what if it's a protein? Well, the molar mass is so big, conventional methods can be pretty tough. So they actually use osmotic pressure to do that. Now you said, well, where's molar mass in the formula? Here's the molar mass right here. So you see it was contained within M for molarity. So what we could do, as we did before, is we could expand this formula by changing molarity into moles per liter, and then we would have grams over mole. Let me write it down for you here. So molarity would be moles per liter. And then we can go from this, we can go to moles is grams over the molar mass times liters. So here's our molar mass down here. So we could actually take this thing and put it right in here and just drop out that M, and then we could solve the equation for molar mass. So simple algebra, but I'm sure you could do that. Okay, so here's an application of osmotic pressure. You may have a relative or know somebody that has to undergo dialysis because of kidneys not working properly. So just follow the diagram. Impure blood is pumped out of the person, right? And it's put into this dialyzing solution through these tubes, and the tubes have a semi-permeable membrane. What happens is the waste products then leave and enter the solution, and purified blood comes out. It's a very slow process. It's a machine that does this. People, if their kidneys aren't functioning, they have to come in 2 or 3 times a week to have this done. It can be very painful.